So this is work lesson 3, in which I'm going to connect work with gravitational potential energy. Your textbook shows you how to calculate gravitational potential energy. It says calculate it by simply taking the product of the mass times little g. Little g is your gravitational acceleration. That's 9.8 meters per second squared. And then your height, because gravitational potential energy is directly related to how high you are, how far you've been lifted up. See, if you're sitting on the ground, you have zero gravitational potential energy. If you have an object that's sitting on the ground, the height is zero. The object's not going to go anywhere. So it means it has no stored energy. Stored energy is what gravitational potential energy is. Just like kinetic energy is the energy for motion when you're moving, stored energy is gravitational potential energy because it's the energy that exists due to the force of gravity. And you realize this as soon as you lift the ball up. If you lift this object up a certain height, now it has stored energy because as soon as you let it go, it's going to fall down. That means if it's falling down, if it's accelerating down, that means it must have had some stored energy. So that's what we call gravitational potential energy. Now, there are a couple of changes I'm going to make. Instead of writing GPE for gravitational potential energy, I'm just going to write a U for gravitational potential energy. And I'm going to put a subscript G. I'm going to do that for all these potential energies because later on we're going to talk about a spring potential energy. And instead of writing multiple letters, I'll write a U for the energy and I'll write down a subscript S for spring potential energy. That's the potential energy that exists in a spring when you compress a spring. It has stored energy because as soon as you release the spring, it fires off. So gravitational potential energy, I'm just going to refer to it as a U with a subscript G. I'm not going to refer to it as GPE as your textbook does because later college texts use a U and I want you to get familiar with that idea right now. Remember to keep your mass in kilograms. Remember to keep your gravitational acceleration, 9.81 meters per second squared. Remember to keep your height in meters. Remember to keep your potential energy in joules. So we're going to do the same exercise as we did in the previous lesson. We're going to connect work to a change in gravitational potential energy. So basically I'm showing that a change, delta potential energy, delta UG, stands for final gravitational potential energy minus initial gravitational potential energy. Remember that 0 is the not symbol we use for whenever we're referring to something initial velocity, initial displacement, initial potential energy. So you can go ahead and expand on this equation by plugging in the equation for potential energy. So it's a simple idea that a ball is being lifted up and someone asks you a question, how much work was done to lift the ball up? Well, you had to do work because you have to exert a force upwards. The reason why you have to exert a force upwards is because you're fighting against the force of gravity that is pushing the ball down. So you had to do work to lift the ball up. You did work, you gave energy to the system being the ball, and the ball's potential energy changed. So simply, if you took the difference between the final potential energy and the initial potential energy, you took the difference as this equation shows you. This is the final potential energy. This is the initial potential energy. If you took the difference, that would give you how much work was done. And you're doing positive work while you're lifting the ball up because the force you're exerting to move the ball up is in the same direction as the displacement. You're exerting a force upwards and the ball is displacing upwards. The displacement is the height. So you're doing positive work. The angle theta between your force vector and your displacement vector is 0. So that will come out to be positive work. Now keep in mind, if somebody asks you how much work is the force of gravity doing against you if you move this ball up at a constant speed, well, constant speed means that the negative work has to equal the positive work. So the force of gravity against you would do work against you too, which would give you a negative value. And the reason for that is because the force of gravity is pointing downwards. And if the force of gravity is pointing downwards while the ball is moving upwards, then the angle that exists between the force vector and the displacement vector is 180 degrees. That's the angle that exists between a vector pointing downwards and a displacement vector pointing upwards. And cosine 180 degrees is -1. That's how you get a negative value. But either case, this is a simple equation that connects work with gravitational potential energy. Feel free to use this, it'll be helpful. Future questions will actually ask you to do both at the same time, connect work to change in kinetic energy and a change in potential energy. It's not very complicated, you simply are combining both ideas into one. So the right side will not only have delta K, but also delta U. And you connect that to your work done. So remember, your force should be in newtons. Your displacement should be in meters, your mass should be in kilograms, your gravitational acceleration should be in meters per second squared, and your height should be in meters. This way all your units will be correct and you won't have any trouble working out these problems that relate work to kinetic energy or work to gravitational potential energy.